Good day, I'm Norman Wapper. In this video, we're carrying on with reciprocals, powers of 10, and Euler's totient function. And we're going to look at an interesting algebraic structure associated to a natural number called the unit group. And this is going to sort of solidify or frame a lot of the discussion about just how powers of 10 look like mod a number n, and correspondingly how to anticipate what 1 over n looks like as a decimal with some repeated structure. I want to know how big that repeated loop is. So last time we were looking especially, say, at multiplication by 10 mod 13. And here's a visual way of trying to see what's going on there by thinking about the non-zero numbers mod 13 in a circle, a familiar kind of clock circle. So we'll put 0 somewhere else here, and here are the numbers 1 through 12. Then what we can do is we can think about multiplication by 10 as something that takes a particular number and sends it to 10 times that number. So if we multiply 1 by 10, we get 10, of course. When we multiply by 10 again, we get 9. That's because 10 times 10 is 100, but mod 13, well, 7 times 13 is 91, so we can throw that away, and 100 is the same as 9. So we get this sort of cycle from 1 to 10 to 9 to 12 to 3 to 4, and then back to 1. So it's a cycle of 6 elements. The remaining numbers, let's say we start at 2, then the cycle goes 2, 7, because 2 times 7 is 20, which is congruent to 7 mod 13. And then when we multiply by 10, we get 5, and then up to 11. Then you can check down to 6, over to 8, and back up to 2. So there's another cycle of 6. So we have 2 cycles of length 6, and this sort of explains why the reciprocals involving 13 in the denominator come in 2 sort of families, one associated to one cycle of 6, and the other associated to another cycle of 6. So we'd like to extend this understanding, but in particular we'd like to move to some more general numbers, not just prime numbers. All right, so while that discussion was revolving around multiplication by 10 mod 13, we could in fact, of course, multiply any 2 numbers mod 13. And that's actually an interesting thing to do. And here is the multiplication table when we multiply any 2 non-zero numbers mod 13. So the numbers from 1 to 12. 1 to 12, here's a multiplication table that gives you all possible products. So for example, 4 times 9, that says that's 10. That's because 4 times 9 is 36, and you can throw away 26, which is a multiple of 13, and you get 10. Now this is a very interesting structure because it's a commutative group. We've talked about groups earlier in this series, and they're very nice algebraic structures. You basically have a multiplication like this, which has a few important properties, not a lot, just a few. First of all, it should be associative. If you have 3 numbers and you multiply first these 2 and then this one, you get the same thing as what happens when you multiply these 2 first and then this one, the associative property. Another important property is that there should be a identity element, in this case like 1, which has the property that 1 times anything is just that anything, in either order. That's the reason why the first row and column are very simple in this table. And finally, there should be an inverse to every element. So if you look at any row, say this row here, there should be the number 1 somewhere in it, in exactly one place. That means that 4 times 10 is equal to 1. And we say that 4 and 10 are inverse elements in this group. So that's basically what you require for a group. You need associativity, you need an identity, and once you have an identity, you need inverses for all the elements. The inverse of the identity is just itself. So this is a group, and it has a name, U13, the unit group of 13. And the multiplication by 10 that we were just looking at is really contained in this single row here. So this row is telling us what happens when we multiply by 10. If we multiply 1 by 10, we get 10. If we multiply 10 by 10, we get 12. If we multiply 12 by 10, we get 3, and so on. Okay, so there's actually a lot more information here than just in that multiplication by 10 story. Now, it's a lovely fact that this kind of unit group algebraic structure works not just for a prime number, but in fact for any number, even if it's composite. But for a composite number, we have to do something a little bit more special than we do for prime numbers. So here's what we do when n is a general number. So u of n, well, it's a set of natural numbers k, everything is a natural number here, k, where k is between 1 and n, so starting with 1 included, but all the way up to but not including n. And with the property that k and n are relatively prime. That means they have no common factor. That's what this notation means. K and n are relatively prime. And that set then is called the unit group of n when we give it a multiplication. The multiplication is multiplication mod n, the number we're starting with. Now this turns out to be a group on account of the following two sort of fundamental propositions. The first is that if you have two numbers m and k, which are both relatively prime to n, in other words, they're sitting inside here, then their product is also relatively prime to n. So if m has no common factor with n, and k has no common factor with n, then m times k will have no common factor with n. That's what this proposition is saying. And I'll leave it to you as an exercise to prove it. And the second proposition is that if m and n are relatively prime, then there is another number a with the property that a is also relatively prime to n, and furthermore, m times a is congruent to 1 mod n. This is also an interesting exercise. We have derived enough to be able to figure this out. If you go back in the last dozen or so videos, you'll see the clue there somewhere. So it's an interesting exercise to figure out why that is. So these are the basic two facts that reveal that this is in fact a group. And it's a commutative group because multiplication in this context is commutative. That's a very important additional property that these kind of unit groups have. They are commutative. So let's look at some examples. When n is 2, then there's only one number less than 2, which is relatively prime to 2, which is the number 1. So it's a very simple group. It's a group with one element, and the multiplication is the only thing that it can be. 1 times 1 is 1. When n is 3, then there are two numbers involved in this unit group, 1 and 2. And the multiplication is this. 1 times 1 is 1, 1 times 2 is 2, 2 times 1 is 2, those are all obvious, and 2 times 2 is 1, because mod 3, 4 is the same as 1. Here's the table for n equals 4. Here's the table for n equals 5. That's another prime, so that looks a lot like, well, the 13 example in some fashion. We have all the numbers from 1 up to m minus 1. Here's n equals 6. There's only two numbers which are relatively prime to 6, namely 1 and 5. So this group structure is really pretty well the same as this group structure, just that the labels are different, but as groups they're really pretty well the same. And of course throughout here there's an obvious connection with the Euler phi function, because the Euler phi function counts exactly how many numbers are in these un groups. The Euler phi function is counting how many numbers there are less than n which are relatively prime to n. So 5n is the same as the number of elements in this set u of n. Okay, how about n equals 7? There's the u7 group multiplication table. It's a prime, so we're including all the numbers from 1 to 7, and it's a nice little pattern. We see that there's one number of each kind in each row, in fact in each column, and it's a very pleasant little thing, but I should remind you that the really deep structure involved in this table is the associative law. The fact that if you take any three numbers, like 4, 2, and 6, if you multiply 4 times 2, you get 1, and if you multiply 1 times 6, you get 6. But if you do it in the other order, 2 times 6 first is 5, And then 4 times 5 is also 4 times 5 is 6 again. So we get the same thing this way or this way. There's the U8 group. Phi 8 is 4. U9, that's also interesting. That's a power of a prime. Not quite a prime, but not too far removed from being a prime. There's 6 in that group. And U10 is this one here, which also has 4 elements. But if you stare at it, you'll see that there's something different about U10 and U8. These are not really the same groups. In fact, they're not at all the same groups, and you might like to convince yourself of that. So there's something algebraically sort of subtle and distinguished about these various UNs. So there's a lot to say here, right? We're covering number theory and also group theory at the same time. So if we did this properly, we would have to spend a little bit more time. So what I want to do is just give you an overview of some basic facts, just to tell you enough so that you have an appreciation for what we're doing with this aiming at, understanding reciprocals of natural numbers. So here are some facts about UN. And in a course in number theory, or perhaps group theory, one could prove these facts, and it's quite pleasant to do that, but I'm not going to. So one fact we've already mentioned, of course, very important, that this is actually a commutative group, and another word for commutative is abelian. They mean the same thing. If n is p, a prime, so in the case when we're talking about a prime, then this group UN is a very special kind of commutative group. It's what's called a cyclic group. And what that means is that there's some number m in the group that has the property that the whole group can be expressed as just powers of that single element m. So if we start with m and find m squared and then m cubed and then m to the fourth and so on, and we go all the way as far as we can before we come back to 1, then we've gone through the entire group. Now, such an element is rather special. It's called a primitive element. It's in general not unique, but it's a little bit mysterious how to find such a primitive element for a general prime p. In fact, it's not just a little bit mysterious, it's very mysterious. Okay, so in many cases, the smallest obvious examples of m equals 2 or 3 will work. So if you have a prime p and you want to know what is a primitive element, your best guess is m equals 2. And if that doesn't work, you can try m equals 3. But that doesn't always work, so there's no real good general rule that tells you what is a good primitive element for a given prime and a given unit group of a given prime. Another very important property in this business is this crucial property of the Euler-Toschen function. So if you have two numbers n and m and they are relatively prime, then phi of n times m equals phi of n times phi of m. This allows you to build up or compute phi of bigger numbers from knowing phi's of various factors. And another kind of special case is that when n is actually a power of a prime, say p to the k for some prime p, then the Euler function phi of n has the pleasant formula. It's p to the k minus p to the k minus 1. So basically you take all the numbers from 1 to n and you remove all the multiples of p in that range. Okay, so these are some facts about u of n, or the associated Euler-Toschen function. Now, one more thing that we really need to know is a fundamental fact from elementary group theory. So we haven't done group theory officially, but you will understand the meaning of this nevertheless. So it has to do with something called the order of an element. So if G is a group, rather a general group, and little g is actually a particular element of that group, then we say that the order of G, denoted order of G, is the smallest k, smallest natural number k, such that G to the k equals 1. So you look at just powers of G, and eventually you get 1. And when you do, that first time you get 1, that power is the order of G. And I might say that for us, all the groups we're considering are so-called finite groups. So in the rest of mathematics, people consider other kinds of groups. But from our point of view, a group is intrinsically a finite group. We haven't yet defined what it might mean to be a non-finite group, because we don't have the notion of a non-finite set yet, and maybe we never will, so we'll have to circumvent that and define infinite groups in some more indirect way when eventually we do. But until then, a group means a finite set, a finite multiplication table, everything concrete, specifiable. You see the whole thing right in front of you. All right, so an example that if you look in the unit group of 7, that you can check that the order of the element 2 is 3, the order of 3 happens to be 2, the order of the element 4 is 3, the order of 5 is 6, and the order of 6 equals 2. From this data, we can see that 5 is a little bit special because you need 6 powers of it to get back to 1. That means that the various powers of 5 will cycle through all of the elements of the group. So that's actually a generator or a primitive element for 7. And here then is Lagrange's theorem, one of the most fundamental and perhaps beautiful theorems in group theory, which says that for any group G and any little g in that group G, the order of that element divides the number of elements in the group. All right, so the order of any element is a factor or divisor of the number of elements in the group. It's a very beautiful result. We're not going to prove it. We're just going to lay it out here so you can have a look at it. Okay, we're interested in this problem of trying to understand what the reciprocals of natural numbers look like as repeated decimals. In particular, how long is the repeated part of a fraction 1 over n when you write it out as a decimal. So we're in a good position now to really understand what's going on here. So let's have a look at, first of all, a larger prime. So 139 is a prime. So what should we expect for the length of the repeating cycle in 1 over 139? Well, first of all, phi of 139 is 1 minus that number, so it's 138. And I've given you here the prime factorization of 138. It's 2 times 3 times 23. So the number of elements in the unit group of 139 is 138. All of the numbers less than 139 are relatively prime to it. So the order of 10 in this group should divide 138. If we look at powers of 10 and ask ourselves how many powers do we have to go before we finally get back to 1, that's exactly the order of 10 in this group. And according to Lagrange, that order should divide 138. That's a very powerful piece of information. And we've seen that in previous examples in the last video. But now we have a kind of group theoretical understanding or explanation of it. So there's not that many possible factors of 138 because there's its prime factorization. So let's try some things. Let's have a look at 10 to the 138 first. Well, we're not surprised to find that 10 to the 138 mod 139 is 1. If you raise 10 to the power of 138, yes, you eventually get back to 1 mod 139. So in this, mod 139 is really what's happening in this multiplication in this group. But maybe we can do better. Maybe we can find a smaller power of 10 that will also be equal to 1. Maybe we don't have to multiply 10 139 times, but maybe some factor of this. Why don't we choose the factor, say, 3 times 23, which is 69. So 10 to the 69 mod 139, my computer will tell me instantly what that is. That's 138. That's not equal to 1. So the order of 10 is not 69. Let's try a different factor. How about, say, instead of those two, maybe those two. 2 times 23, which is 46. Well, then 10 to the 46 mod 139, my computer tells me that's equal to 1. So we have found now a smaller possible order of 10 in this group. But maybe something smaller will work. Maybe just 2 times 3. Let's see if that works. 10 to the 6th mod 139 is 34. That's not going to work. So this number 46 is the smallest possible divisor that has that property. The 10 to it is equal to 1. So this is actually the order of 10 in this group. Well, we've seen that's exactly the length of the repeated part of the decimal expansion. And here is the decimal expansion of 1 over 139, 0.00719,424, etc. And you can see it there, and you can count that the number of elements in that repeated segment, and it repeats all the way from 00 up to 41, is exactly 46. And now let's have a look at a more complicated example where we have a composite number. So our n here is going to be this number here, which is the product of these two primes, 163 times 18,301. So what should be the length of the repeating cycle if we look at 1 over this n? Okay, so we're going to proceed as before. First of all, we look at the Euler-Toschen function, phi of n. So n is a product of these two things. These are relatively prime. So this is going to be phi of 163 times phi of 18,301. Because these are relatively prime. And phi of 163, well, that's a prime, so its phi function is just 1 less than it. This is also a prime, so its phi function is also 1 less than it. And so the product of these two is this number here, which is important for us to have its factorization. There's its factorization. It's 2 cubed, 3 to the 5th, 5 squared, times 61. Okay, so we're interested in what is the order of 10 in this group, in the group U of n. So this is a bigger group now. If we had to write out the multiplication table, it would be a very big table because it would have this many rows and columns. But we can do calculations in it just by making calculations mod n. So we're interested in what power do you have to raise 10 to get 1. That's the magic number. So we start with the full number here, and we just check that when we take 10 to this number, to phi of n, we get 1 mod n. That's as it should be. That's what Euler's theorem tells us, because 10 and n are relatively prime. Okay, so now we have the idea that we're going to look at smaller possible numbers, and we're going to get those smaller numbers by throwing away some of these prime factors to ensure that we still have divisor of this thing. So let's throw away 61. So now we just have 2 cubed, 3 to the 5th, 5 squared, and we look at this thing mod n, and we find that it's this thing here, which is definitely not 1. Okay, so we put the 61 back, and we think about the 5. Maybe we'll just throw away a factor of 5. And we'll just have a 5 there instead of 5 squared. When we calculate 10 to that power mod n, we also don't get 1. So no problem, we put the 5 squared back. And we think about the powers of 3. Let's lower the 3 to 3 to the 4. Well, that turns out to give us 1. But if we lower it 1 more to 3 cubed, it turns out that we don't get 1. So we can lower it by 1 and we're okay. Finally, what about the powers of 2? If we lower the 2 cubed to a 2 squared, and we'll still keep this 3 to the 4th, then this thing mod n is equal to 1. And if you do it one more time and lowering it to just 2 times all of this, then you see that in fact you don't get 1. So this ends up being the smallest number that we can find, such that 10 to this power mod n is equal to 1. And that's telling us that the answer to our original question is that the order that we're looking for, or the length of this repeating cycle, will be 2 squared times 3 to the 4th times 5 squared times 61, which is 494,100. Telling us that if we look at 1 over this number, that's going to repeat with a period of 494,100. Okay. Okay, so we're in a great position now to understand what happens with Z. That's what we're going to do next time. And we're going to address the question of why does the unique factorization break down for Z? And was Euclid wrong? What's actually wrong with Euclid's proof? Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.